going to be looking at 2.4. Does anyone have homework questions before we do that? So we started looking at section 2.4 when we looked at figuring out a date. So we had Friday's date, and we were trying to use that to figure out what day of the week the 4th of July fell on. So what we did is we took out weeks. We took out groups of 7. That kind of counting is called modular arithmetic, where you take out groups of 7 or groups of 12 or groups of whatever. This happens when we take out groups of weeks, because those go in 7s. But another place that would show up would be with clocks, right? When we count time on a clock, if we have a 24-hour clock, when we get to 24, we don't go to 25. And if you have just a 12-hour clock, when you get to 12, you don't go to 13. So this kind of taking out sections, groups of numbers occurs in our cyclical nature that we have. So in this section, we're going to explore ideas systematically and investigate consequences and formulate general principles. Well, let's start. Let's take a look at clocks. So let's go ahead and draw a 12-hour clock. They say the better you can draw a freehand circle, the more likely you are to be a good artist. So we know where that puts me, but hopefully you're doing better at circles. So suppose it is 10 o'clock. Suppose it is 10 o'clock. What time will it be and then we'll have a number of different times. So we'll start the first one off at A. Suppose it's 10 o'clock. So we'll put a little hour hand at the 10. What time will it be in 38 hours? So some of you can just do that in your head. Does anybody have the answer? Now you could just count off, right? 1, 2, 3, 4, 5, all the way around 38 hours. Another way would be to take out multiples of 12, because every 12 hours you're going to be back at 10. So that's a little faster. So if we take out multiples of 12, we can do that 3 times. So go around the clock 3 times. 1, 2, 3. And that is only 36 hours, so we need 2 more. This isn't equal to 12 o'clock. Equals mean things, so I'm not going to put equals. Let me just cross that off, okay? But 12 o'clock is the answer. If we start at 10 o'clock and we move 38 hours around the clock, then we get to 12 o'clock, because we go around 12 hours 3 times, and that keeps putting you back at 10, and then you go 2 more hours. How about in 22 hours? So we start at 10 o'clock, and we're asking, what time will it be in 22 hours? Anybody know what that would be? Yeah, good. 8 o'clock. 8 o'clock, right? So your 22 hours, you go around the clock 1 time, 1 12-hour section, and then another 10 hours after that. So you can just count off the 10 hours. And that puts you at 8 o'clock. Now you could also think, well, that's 2 hours less than a whole day. So 2 hours earlier. Is that maybe how you thought of it? Yeah, I think that's a little faster on this one. Well, let's go for a bigger number. 412 hours. So it's 10 o'clock. What time will it be in 412 hours? And I think this is a good time to take out your calculators if you haven't. We'll be using our calculators quite a bit today. So we want to take out multiples of 12. So we divide 412 by 12 to see how many times 412 can be divided by 12. We get 34.3 repeating. And that means you can go and take out 34 multiples of 12. So how many hours would that be? We'll go ahead and find out. We'll take the 34 times the 12. 408. So we can go around the clock 34 times, taking out multiples of 12 hours out of the 412 hours altogether. And by doing that, we take away 408 hours. And that leaves 4 hours left after that. So we're going to go 1, 2, 3, 4 more hours to 2 o'clock. So we're at 10. We keep going around the clock, multiples of 12 hours, so we keep landing back at 10. Then when we take away all the 12-hour multiples that we can, we still have 4 hours left. So 1, 2, 3, 4 to 2 o'clock. So 412 is 12 times 34 plus 4. So the idea of the clock is to give what we call modular arithmetic a face so that you can picture what's going on. We're going to use a clock now with 7 hours. So we'll draw a clock with 7 hours at the top and then try and put the other hours evenly around it. So now we have a 7-hour clock. So on this clock, if it is 2 o'clock, what time will it be And first we'll try just 7 hours. Okay, so it's 2 o'clock. The hour hand set at the 2. 7 hours go by. What time will this clock read? 2. Good. 2 o'clock. So you get right back where you started. 1, 2, 3, 4, 5, 6, 7. Okay. How about if 12 hours go by? Good. Yep, 7 o'clock. So if 12 hours go by, you go all the way around the clock, but that's only 7 hours on a 7-hour clock, and then you go 5 more. 1, 2, 3, 4, 5. So that brings you to 7 o'clock. You go all the way around the clock one time, and then you keep going and go 5 more hours till 7 o'clock. You have to try some big numbers too, okay? How about 211 hours? See if you can use your calculator to help you figure out. If you start at 2 o'clock on a 7-hour clock and you go 211 hours, where does that put you? Well, you would take your 211 and divide by multiples of 7 that you wanted to take out of there. So that's 30 times. You can take out multiples of 7. And then 30 times 7 is 210. So by the time you take out 30 multiples of 7, you've taken out 210 of those hours. That means you're only going to go one more hour to 3 o'clock. So did you have 3 o'clock? If you had 3 o'clock, pat yourself on the back, okay? Does anybody have any questions on this? What we're doing with this is called modular arithmetic. So we're going to practice a little modular arithmetic, and then we'll see what it's used for. So instead of drawing a clock from now on, we'll just put this in the math terms that you would use for modular arithmetic. So what we're going to do, for example, is check out what 25 is equivalent to in, leave a little line here, we'll fill that in mod 7. These are problems that you'll have on your quiz, doing modular arithmetic. So we want to make sure everybody gets the hang of that before we move on. So 25 is equivalent to what mod 7? So basically we're starting at 0 on our clock there and going 25. 7 and 0 would be equivalent. But let's see where that brings us. Okay, so we take the 25 and we divide by 7 so we can take out multiples of 7. I think the screen froze. So we take out multiples of 7. And we see we can take out 3 multiples of 7. 3 times 7 then is 21. So we're taking away 21 units when we take out 3 multiples of 7. 25 minus 21 is 4. So we're saying that 25 is equivalent to 4 when you're looking at modular 7, a mod 7 clock. So if you went around this clock starting at 0 at the top, which is also 7, you went around 25 hours, you'd end up at 4 o'clock. So when we do modular arithmetic, it's really, sometimes I think of it as remainder arithmetic because you're looking for the remainder. You're looking for the remainder when you take this number on the left and divide it by this number on the right. Let's try another one. How about 25, but this time we'll say it's equivalent to what mod 4? So we want to know what number is 25 equivalent in mod 4 arithmetic. So we're going to take out multiples of 4 this time. So take the 25, divide it by 4, get 6, what do you get, 6 point what? 6.25. So we can take out 6 multiples of 4. And when we do that, when we take out 6 multiples of 4, we're taking out 6 times 4, or 24. And that leaves 1. So 25 is equivalent to 1 mod 4. Does anyone have questions so far? Your answer here should always be a number smaller than the number on the right, because it's a remainder, right? So your remainder is always smaller than the number you're dividing by. How about a big number? 416 is equivalent to what mod 8? So we're going to take out multiples of 8. When I put that in my calculator, 416 divided by 8 is 52. No decimal point. That's because when I take 52 times 8, I get 416. So this time, there is no remainder, and that means 8 is equivalent to 0. I'm sorry, 416 is equivalent to 0 mod 8. That's why up here I was saying on the clock that the 7 and the 0 are equivalent, because 7 mod 7 is 0. So this modular arithmetic, where we put the remainder down after we take multiples of the number on the right from this is used for a number of different activities. Here's some examples. So this is your textbook. Your author is calling that crazy clock arithmetic. It helps us find errors in grocery prices, our checking accounts, UPS package deliveries, airline tickets, and driver's license numbers. So besides being able to use modular arithmetic for those ideas, you're going to get some on the quiz. So let me put down a few problems for you to try right here in class and make sure you understand how to do this. So these are just what they'll look like on the quiz. There'll be a number, there'll be an underscore, and then it'll be what mod. Does anyone remember having to do these in school, in grade school? We did. I remember doing them in grade school. All right, 210 is equivalent to what mod 7? 327 is equivalent to what mod 4? And 9 is equivalent to what mod 8? So go ahead and find those values out, and Nicholas and I will walk around and give you a hand if you're stuck. So if you're stuck, raise your hand. Or even if you want to have your answers checked, go ahead and raise your hand too. It's kind of weird because you write it the other way, right? Yeah.
So I need to find a replacement. I'm asking about it.
What's amazing is that you took the 80 times and the same. I think. A whole group.
So here's how my day tomorrow. I have to wake up 5:30 in the morning to be at the studio at 6
If you're stuck, raise your hand.
I'll be there. Because I don't fall asleep until like 1:30 in the morning for coffee.
So when you take the number and divide by the number out front, remember, don't write the decimal that you get down, just the whole number. Okay, so you write the whole number part down, and then 81 times 4 is 320, and you can subtract. Whoops, that didn't work. 324. There. Okay, you should always get a number smaller than the number on the end there. And this one maybe you could do in your head, right? Because 9 is 8 plus 1. So think of that modular clock starting at 0. If you had any questions on any of these, make sure that you clear them up with myself or a tutor, okay? We want you to get hundreds on your quizzes. At least that's what I want. Is that what you want, Nicholas? Yeah. That's what Nicholas says. Then let's take a look at some UPCs. So I brought a couple of UPCs of my own, but once we get started, if I can, we'll use some of your UPCs if you have any with you. So this is a Kleenex box, and on the Kleenex box there's the universal product code. The first 6 digits are to identify a manufacturer. So if you have another Kleenex product, it more than likely starts with these first 6 digits. And then the next 5 digits are for the Kleenex company to identify their own item. So their internal use to the Kleenex company. And the last digit is called a check digit. And that's where our modular arithmetic comes in, finding the check digit. So we're looking at UPC codes that are 12 digits long today. And let's write the first one down. And as we write it down, we'll need lots of space between the numbers because we'll do arithmetic with it. So I'll put it up here again, and I'll read it. Maybe if I take the light off, it'll be, yep, that's better, isn't it? You do need to start with that little number at the beginning there, the 0. So 0, 3, 6, 0, 0, 0, 2, 1, 4, 0, 0, 0. So the first 6 digits are to help the company be identified. The next 5 digits are for the company's use. And then the last digit is the check digit. So the check digit helps to make sure that numbers aren't transposed when you're typing or talking about these numbers, or that you don't accidentally mishear a number. The check digit, if the check digit is not what it's expected to be, a computer can test that and know that. Okay, so let's go ahead and see what the code, how the code works. What we do is we have this little pattern that we do. We say times 3 for the first digit, times 1 for the next digit, times 3 times 1, and we just repeat that. Times 3 times 1, times 3 times 1. So hopefully you left enough space for that. So we just multiply each of the digits in this pattern. Times 3 times 1 times 3 times 1. The last number, the check digit, would be times 1. So you can write that if you want to, but it's not necessary. So 3 times 0 is 0. 1 times 3 is 3. 3 times 6 is 18. 1 times 0 is 0. 3 times 0 is 0. 1 times 0 is 0. 3 times 2 is 6. 1 times 1 is 1. 3 times 4 is 12. 1 times 0 is 0. 3 times 0 is 0. Once we do this times 3 times 1 times 3 times 1 all the way across, we add these numbers up. So I'm going to be giving you a UPC on the quiz also, and you'll have to find the check digit that's going to be missing. So hopefully you can understand this. It's not too bad. So we add all these numbers up and see what we get. Did anybody else get 40? Yep, okay. And then we would add the check digit. This time it's kind of a boring number. And we get 40. This is called the check sum. It turns out that the check sum is always equivalent to 0 mod 10. So that's how the check sum, that's how the check digit works. After these first 11 digits are used to code what the item is, then the check digit is added by the manufacturer to make sure that if any of these numbers are misread, you'll still get a number mod. You won't get a number mod 10, and then you'll know, okay, there's an error here. Somehow something happened. So you notice that 40 is equivalent to 0 mod 10. The mod 10 is the easiest, right? You just have to take off multiples of 10, and so whenever your number ends in a 0, you know you have 0 mod 10. So that's the check digit. It's kind of boring when it's 0. So now we'll do one of yours if you have any. Does anybody have a UPC code? Beverages like Coke and such don't always work. So I'd rather not use a beverage if there's anything else. Do you have a UPC? Okay, tell us everything but the check digit. So don't forget, do not tell us the last number.
Okay. 8 2 5 4 6 6 9 8 0 2.
Okay, and then there's a check digit here. So we're going to, right?
Yep.
And we're going to tell what the check digit is by our work here, because we're going to know it's whatever number we need to add to get to the next multiple of 10. After we do the times 3 times 1 times 3 times 1 stuff. So times 3 times 1 times 3 times 1, and so on. So 3 times 8 is 24, 1 times 2 is 2, 3 times 5 is 15, 1 times 4 is 4, 3 times 6 is 18, 1 times 6 is 6, 3 times 9 is 27. You started with the little bitty number, right? The little tiny one?
Yeah.
Okay, thanks. 1 times 8 is 8, 3 times 0 is 0, 1 times 0 is 0, 3 times 2 is 6. It pays to check your arithmetic as you go along here. Let's see what we get. Did anybody else get 110? Yep, you got 110? Okay. So what does that make the check digit? 0. Yeah. Was it 0? Okay. Check digit was 0 because this is 110. 110 is already equivalent to 0 mod 10. Well, so now I'm going to try and get one that's not 0. I have a couple up here, but as I said, it's more fun. Does yours not end in 0?
Yeah, it doesn't. It doesn't. It doesn't end.
It doesn't end in 0? Okay, but it's a beverage, so it still might not work. Okay, so we'll do this one. Can you read it all but the check digit?
Okay. 0 1, 2, 0, 0, 0, 0, 2, 1, 3, 6.
All right, thank you. So let's do that times 3 times 1. Times 3 times 1 times 3 times 1 times 3 times 1, all the way to the end. So 3 times 0 is 0, 1 times 1 is 1, 3 times 2 is 6, 1 times 0 is 0. These are all a bunch of zeros, those are always nice. 2 times 1 is 2, 3 times 1 is 3, 1 times 3 is 3, 3 times 6 is 18. What does that add to? Anybody else get 33? Okay, 33. So what does that mean the check digit needs to be? What is it?
Check digit needs to be 30, right?
We have to get to the next highest multiple of 10.
Okay.
So from 33 up to 40. So it would be what? 7. Yeah, 7. Yeah. Okay, so the check, was it 7?
Mm-hmm.
Okay, so it is 7. Thanks. So the check digit has to be 7 because we want to get to the next highest level of 10, because then your checksum, again, this is called the checksum. Wiley will talk about your checksum, and that's what it's referring to. Your checksum equals 40, and 40 ends in a 0 because it's 0 mod 10. So I will ask you to do one of these on a quiz. Does anybody want to do another one? Okay, then if you want to take out a camera and upload this is your class activity. The quiz, the one I was thinking of was the Kleenex box, but you can upload any of these. Yes, don't forget to put your name placard in there. Either yourself or your name placard should be in there. Or you just handwrite your name, I guess, would be all right. Then we're going to look at checks. So this UPC check digit, if a single error is made, such as a number read incorrectly or typed incorrectly, the check digit will always detect the error. Now a check needs a more robust checking system, right? Does anybody else want their IRS refund to go to their account? Okay, not to somebody else at the bank. We're actually checking the routing number, so we'll at least make sure the check's getting to the right bank. So the routing number is this digits over here on a check, and I brought a check along. But the method that we're going to use on a check is more robust. As I said, it will catch any one error and is able to catch most switches of 2 consecutive digits and even most switches of 2 digits one apart for another. So that's more rigorous. So here's a check. We're going to write down the routing number. That's the numbers on the left over here. 9. So let's write checks so you know it's different in your notes. 091. Gotta leave space. 091 with some space. 091 981 811. So for a check, the check digit, this 1, comes from this process times 7 times 3 times 9 times 7 times 3 times 9 times 7 times 3 times 9. So a little harder, a little more arithmetic. 739, 739. So 7 times 0 is 0, 3 times 9 is 27, 9 times 1 is 9, 7 times 9 is 63, 3 times 8 is 24, 9 times 1 is 9, 7 times 8 is 56, 3 times 1 is 3, and 9 times 1 is 9. So this also needs to come out to 0 mod 10. What does that add up to? Anybody else get 200? No? Okay. So on the check routing number, the checksum does need to be 0 mod 10, just like it did on the UPC code. But the way you get to that checksum is different. So you'll use both of these methods in Wiley Plus. So I wanted to make sure to show them to you. The one that you'll have on the quiz will be this one. Okay. So the quiz one will be the UPC one, but you'll have both types on Wiley Plus, so you can have some practice with both of these. When you're just finding the check digit, it's not too bad. If you have to find the first digit, it's a little more work. Like on this problem, for example, you're trying to get up to add, and so that you have a number ending in 10, and then you have to think, but wait, I'm taking a multiple of 3. So then you have to think of multiples of 3 that will put you up to a number when you add that's 0 mod 10. We can certainly go over those as you have questions on them in your homework there. We're going to go on to the next section, 2.6. We're going to need to review a little algebra in that section. We're going back to chapter 2, looking at numbers, and 2.6 we do some algebra before we actually get to the topic in 2.6. We're also looking at fractions in 2.6, so we'll review those a little bit. So when you take and divide a circle in half, you've divided into 2 pieces. And so the bottom number on a fraction tells how many pieces you've divided this one item into. If I divide a circle into fourths, then each of those pieces is one of the 4 pieces, and that's why we have 1/4. So the bottom number tells how many pieces you have divided one item into. And then the top number tells how many there are. So if I took 3/4 of that circle here, I would say 3/4 because I have 3 of the quarters making up that shape. So the bottom number tells how many parts you divide into. The top number tells how many of those parts you're looking at. Fractions can have different names and mean the same amount, right? If you took the 1/2, how much of the circle in fourths is that?
2/4.
Yeah, 2/4. So these are equal. So same value, different names. When you have the smallest numbers you can, that's called reduced. And the way you reduce is pretty straightforward. You look for, well, let's try one. You look for a number that divides into the numerator and the denominator, like maybe 3 here. And you go ahead and divide the 3 out. So 15/18 is equivalent to 5 divided by 6 because there was a 3 in the numerator's factorization and a 3 in the denominator's factorization that you can divide away. just like what we did up here, the 1/2 and the 2/4, you could think of the 2/4 as a 2 times a 1 and a 2 times a 2, and you can divide away the 2 over 2. So 2 over 2 is just 1, and that's why you can divide it away, because if you take something and multiply by 1, it's still the same value. 3/3 is just 1. You can divide that away. So we'll be looking at fractions that are reduced. We won't be doing too much hard things with it, just making sure you know what that means. We'll also be looking at roots. So that square root symbol, when we have the square root of 4, what would that be? 2. Good. Yeah. 2. And that's because 2 times 2 is 4. Square root of 4 is 2 because 2 times 2 is 4. Or the square root of 25, what would that be? 5. Yeah, good. Because 5 times 5 is 25. So when you talk about a square root, you're talking about the number that you can multiply times itself to get the value under the symbol. Now, if you have something like the square root of 7, well, there is no number that's a nice number that you can multiply times itself and get 7. So that we would just leave that, and we'd say that's the exact value of the square root of 7. We would just leave it the way it is. At least mathematicians would. If you're in physics now, you want to know what that is approximately. So you take out your calculator. You get the approximate value. $2.645751311. I wrote down all the digits. Why is it still approximately? Shouldn't that be exactly what the square root of 7 is? It's still, pardon?
Oh, it's not a whole number.
Right. It's not a my calculator rounded it off too. So my calculator rounds off farther than I usually do, but it's rounding it off, or it might truncate it. Mathematicians like the exact values because when you round things off, this round off error can quickly add up to be very large if you're doing a number of computations. So that's what we mean by a square root. We also should review solving. So we're going to solve just a simple equation, just as a reminder of the steps that we take. So we're going to solve 2 times x plus 3 equals 5, and that just means finding the number that x is that makes the equation true. What would you do first if you're solving this? Anyone remember? Let's see ahead.
Take 3 and subtract 3 from 3 and then subtract 5 from 3. And then that would, the 3 and the 3 would cancel out.
Right, exactly. So we're going to subtract 3 from the 3 and 3 from the 5 because we're trying to get that x by itself. So you have 2x equals 2. So what we did there is we made sure what you do to one side of the equation, you do to the other. So whatever you do to one side, do to the other also. That's how you keep an equation true. Okay, so whatever you do to one side of the equation, do it to the other also. And that will keep the equation true because an equation is like a balance scale. Anybody use a balance scale in physics or chemistry? You had to put the same thing on both sides, right? So this equals is like the balance. Both sides are equivalent. And if I keep the same process going to both sides, it'll stay equivalent. So here I subtracted 3 from both sides and got a 2 and a 2x, and they're still equal. What's the next thing to do? You probably already did it, right? What'd you do? Yeah, divide both sides by 2. And again, whatever you do to one side, do to the other. So I just wanted to remind you that when you work on one side of the equation, you work on the other. If you're going to do something to one side, do it to the other also. Now this might be new to you. Consider prime factorizations that are squared. Okay, so let's just start with the number that's not squared. Let's take 136 and find its prime factorization. 136 is even, so I'll go ahead and divide a 2 out. Two times 68. 68 is even, so I'll divide a 2 again. And 34 is even, so I'll divide 2 out again. So we end up with 136. It's 2 times 2 times 2 times 17. Now let's take 136 and square it. That's a big number. A 136 squared is 18,496. Can you tell me what the prime factorization is without doing a bunch of arithmetic? Of 18,496? Yes.
I don't know if this is right, but 2 times 2 times 2 times 2 times 2 times 17 times 17?
Perfect. So what did you do?
I just doubled the prime factorization of the original number.
Good. Double the prime factorization of the original number, because this is, you could do for your first step 136 times 136, and you already did the 136. Okay, perfect. Let's try another one. How about 54? So go ahead and find the prime factorization of 54. So 54 is even, so you could divide a 2 out. It's 2 times 27. And 27 is divisible by 3, 3 times 9. And 9 is 3 times 3. So the 54 is 2 times 3 times 3 times 3. Now let's look at 54 squared, because that's our topic. Prime factorizations squared. So 54 squared is 2,916. So if I asked you to find the prime factor of 2,916, you could write that down, right? Everybody could write it down now? Okay, because you can just think of it as 54 times 54, so you write down all that you had before 2 times. Okay, so 2 times 2 instead of 1, 2, and then 3 times 3 times 3, and then another 3 times 3 times 3. Well, the point of all of that was to point out that the prime factorization of squares always has an even number of factors. The prime factorization of squares always has an even number of factors, because you take the prime factorization of the one number and you just double it, because that's what a squared is. It's a number times itself. So its prime factorization times itself makes twice as many factors. So I didn't even count how many there were, but Oh, 8, yeah, 8 here, and then 8 there as well. I should have picked something that wasn't just 8. Well, we're going to use all of these ideas together when we get to, more deeply into section 2.6. We'll be doing that on Wednesday. I'll see you then. Pardon?
That was quick.
I might have gone too fast. If I went too fast, see me after class and we'll go over any questions you had, okay?
I'm in time for class really fast. I'm like,
Go ahead. Better than like, oh.
yeah. That's how it was. Yeah. It's actually interesting.